I'm scientific director in IMEC, the Netherlands. I'm also the principal investigator of the ERC-funded project Intranet of Neurons. And I would like to first acknowledge the funding from ERC, the European Research Council, and also the contribution from the team Intranet of Neurons. Our brain is the most complicated object in the known universe. It has 80 billions of neurons. That is the same number, almost the same number of the planets in the galaxy. And even more, each neuron has thousands of connections to other neurons. So it's extremely complicated network. It give us a feeling that we are a very unique individual and we have conscious, but we have quite little idea about how exactly our brain functions. In addition, 1 out of the 6 world population suffering from neurological disorders. Due to the lack of knowledge about how our brain exactly functions, many of these mental disorders cannot be properly cured, and sometimes even not objectively diagnosed. So we try to develop many sensing technologies in order to understand our human brains. Okay, I would like to show you the outline of this talk. First, I will talk about a very important neural sensing technology, intra-cortical neural recording. Then I will talk about the wireless communication especially for the brain-computer interfaces, intra-cortical BCI. And here in this topic, I will especially focus on 2 challenges. One is size reduction, and second is about data reduction. Then I will zoom into very important topics called spike classification, and especially we want to talk about how to do that on implants. For that, we have to carefully trade off between communication and computation. I will also use example with nerve conduction study with an implant to discuss this communication versus computation trade-off. And finally, I will give brief conclusions. Intracortical neural recording. There are many sensing technology that were already developed to help to understand the brain. And one popular method is the imaging method called functional MRI. It provides colorful image on the area of the brain that are currently active under certain activities. It provides a macro view about how human brains functions, overall brain-wide, but usually it does not provide sufficient detail. It is similar to that we use a telescope to observe the universe. We know something happening somewhere there, but we don't know exactly what happened at which places at which time. In order to know more, we send the rovers, for example, to the Mars to take the pictures, very high quality pictures, and then send it back to the Earth for further analysis. Similarly, we can also place the sensors, neural sensors, in the cortex to record the electrical activities of single neurons with high quality. And such intracortical neural sensors is shown. One example is shown here. This is FDA approved, one of FDA approved intracortical neural sensors with micro-electrode array. So intracortical neural recording is recording the neural activities next to the neurons, that also called extracellular neural recording. So here is one example waveform of the extracellular neural recording. X-axis is time, Y-axis is the channels. In here, just show tens of channels. In practice, they can be up to hundreds or even thousands of channels recording. And here is when the neuron is active or is firing called spike. One recording channel can pick up the spike from multiple neurons, and each neuron has its specific spike waveform. In order to be able to recognize which spike corresponding to which neurons, we need to preserve the spike waveform as detailed as possible. So spikes typically are very narrow, hundreds of microseconds. So we need to sample with a sufficiently high data rate up to tens of kilohertz. In addition, to keep the detailed waveform feature, we also need to have high dynamic range ADC, typically above 10 bits. So this can easily introduce a large amount of data. And that is the challenge when we want to use a wireless interface to transfer all of this data. And next part, I would like to talk about the wireless communication, especially for intra-cortical brain-computer interfaces. The brain-computer interfaces was introduced 1970s from UCLA. So it is BCI is a communication pathway between the brain and electronics. In 1990s, UC Berkeley shows that they use intra-cortical neurosensors placed in the brain to have intra-cortical brain-computer interfaces, and that achieve a very good recording and decoding qualities. Nowadays, it's possible that we can use intra-cortical BCI for future therapeutic purpose as neuroprosthetics. One example is the motor BCI to restore the movement. Another example is that BCI can be used to predict the thought of the patient who cannot speak and then type on the screen. So these two are just some examples of intracortical BCI, and you can imagine this can be a very powerful technology potentially that can help patients with neurological disorders. However, there are still many technological challenges to be overcome. This slide shows the evolution of IBCI in the past decades. Starting from 2006, Brown University, they show such kind of BCI devices with a head-mount device with long cable connect to the computer. And at the time, they can record roughly 100 channels of neurons of channels. And 2 years ago, Brown University showed a wireless version of it, and now they can record up to 200 channels. Recently, there are more and more star companies also trying to develop the fully implantable version of IBCI, and they can record even more than 400 channels. So from this evolution, you can see two important trends. One is that it is becoming less and less invasive. And in here, wireless interface is a critical part to make IBCI clinically viable, because we can avoid infection risk, and also we can make the IBCI device stay in the body for a much longer period of time. The second trend you can see is the number of recording channels also keep increasing. This is because there's a strong demand that we want to interface more neurons. So if we follow this trend, we can see what's next for the future BCI in 10 years. First, we can already see that from the recent literature that neuroscientists would like to record the brain activities brain-wide distributed. So a few groups that has shows that they try to insert multiple intracortical neurosensors in different parts of the brain of the animals. And we believe that different regions of the brain are actually highly interactive and have a very high correlation. So such a brain-wide distributed recording can help us to know better and how our brain functions. Second important trend is that such a brain implants should be free floating. The reason is that brain has micro motion of several millimeter. And if there are wires connecting between the brain implants and the scale device, the wire can cause the shift of the electrode, intra-cortical neurosensors, and this can cause the motion artifact during the recording. Second is that if there are wires connected in between with a micro motion, you can cause the potential scar tissue, and the scar tissue can block the intra-cortical neurosensor and gradually degrade the recording quality over time. In this paper, we show that we can use a two-stage wireless link with extra link called transdural link to completely get rid of the wires in between the scale device and the brain implant, such that we can make that free floating. Okay, now let's dive a bit deeper. What is the exact challenge in order to work toward the future BCI? First, we want to see the minimum invasive from the surgical perspective. Craniotomy is a surgery that opens the skull. Traditionally, craniotomy opens the skull hole up to several centimeters, which is very invasive. And recent craniotomy can open, such as burr-hole craniotomy or even twist-reel craniotomy, can open the skull hole even below 1 centimeter in diameter, which is such that the patient can recover much faster in just a few days. But also means that the brain implants should be designed with a footprint much smaller than 1 centimeter squared. This brings another potential challenge, that is tissue heating. Tissue heating can come from the power consumption, power dissipation from the electronics. From Gasoliers, their work, they shows that they simulate the tissue temperature the surrounding tissue temperature increase when electronics is implanted, and they notice that the tissue temperature increase is affected by the size of the electronics and also the power consumption of the electronics. In another work, in another paper, they also study also provide a typical guideline when we design the electronics. We should ensure the heat flux should be smaller than 40 milliwatt per centimeter square, such that we would not increase the tissue temperature by more than 1 degree. And important to note that in typical brain implants, the wireless communication part dominant overall area and also the power consumption. Now we switch to another direction. While we want to minimize the invasiveness, we also want to maximize the data rate. Here I would like to quote one statement from a UCLA professor: "Everybody always wanted more neurons." And especially here, I assume that everybody means the neuroscientist. But here is also support from another survey from Stevenson's lab, showing that the number of simultaneous record neurons double every 6.4 years. And that is already since 1960s. And this trend even speeding up with the introduction of silicon-based intra-cortical neurosensors. For example, IMAX neuropixels, which leverage the advancement from the semiconductor technology. Not only the neuroscience experiment, but also the IBCI for potential therapeutic purpose. The BrainGate project funded by DARPA shows that if we are able to decode roughly 100 neurons, we can control the arm or prosthetics to perform grasping. If we want to do finer movement, such as tying shoelace, it is estimated that we will need to decode up to 10,000 of neurons. For the full body movement, this can even go up to 100,000 of neurons. So as you can see, recording and decoding large amount of neurons can create huge amount of data. This becomes a problem of big data in a very tiny brain implants. So we want to have a high sampling frequency and high dynamic range ADC in order to keep the spike waveform feature. We also want to increase the number of recording channels. So this can easily end up with a minimum data rate of 250 megabit per second. To know that this is equivalent to a data rate when the Wi-Fi is in the Wi-Fi connection with a very optimal condition. And now we are talking about we need to handle this with a very tiny implants. So here I also performed a survey with the many implantable transcutaneous wireless interface, wireless radios with the data rate versus module area. And you can see there's a general trend that if you want to achieve higher data rate, you will need to have a bigger module area. This is mainly due to the antenna property, which I will talk about a bit later. Now we are talking about we want to push that to this point, tens of millimeter square area, while hundreds megabit per second of data rate. This requires several order of improvements. And first, we would like to look at the size reduction. And here we will talk about antenna-less wireless communication. And another direction is to reduce the data, and especially we want to do lossless data reduction. For here, we will talk about neuron-inspired neural encoding approach. So first, let's talk about the size reduction. Here shows the state-of-the-art the wireless interface for the IBCI, and impulse radio ultra-wideband is considered one of the most promising wireless communication method for IBCI. The impulse radio can achieve a very low energy consumption because it just transmit the pulses, and the frequency control and phase modulation circuits can be greatly simplified. Typically, the impulse radio can achieve the energy consumption in the order of tens to hundreds picojoule per bit, which is quite low energy. Also, impulse radio ultra-wideband can achieve a high data rate because they can operate in the frequency band called ultra-wideband, which has several gigahertz of bandwidth available. And in our recent work that we present last year in ICC shows that we use 1 gigahertz of bandwidth and we modulate the amplitude of the pulse, position of the pulse, and also the phase of the pulse. We can achieve up to 1.6 gigabit per second of data rate, which is a record from the literature. But there's still one limitation, that is the footprint area. This is because the ultra-wideband typically require at least 1 centimeter square of area if you want to ensure there's sufficient radiation efficiency. The reason I would like to use this slide to briefly explain. So we know that antenna, if we want to have a good radiation efficiency, it should design with a geometry roughly match to the wavelengths. And here I would like to define the quality factor Q of the antenna to be center frequency F0 divided by the bandwidth, and you can approximate with this equation. And K is 2 pi over lambda, the wavelength is lambda. A is the radius, and Ka means the ratio between the geometry and the wavelengths. If we have a small Ka, which is electrically small antenna, then you are going to get high quality factor. High quality factor means your bandwidth will be limited. Of course, we can consider to also maybe increase the center frequency F0 with a given Q, you can still get a large bandwidth. The issue is that when you increase the frequency of the antenna and the electronics power consumption will increase, and the tissue will tend to absorb more energy, radiation energy from the antenna. So this will lead to tissue heating. So from the antenna perspective, you can already see there's a trade-off between the area, efficiency, and the bandwidth. So the question is that can we design a antenna-less wireless communication? Here, we would like to be inspired from the biology. So we probably still remember high school physics. If you apply 2 voltage in the salt water, this positive charge in the salt water is going to flow toward the electrode with low voltage, and vice versa, and this will create so-called ionic current. And neuron is how neuron use the ionic current to propagate the spikes, which can be very fast, and this may indicate there will be sufficient bandwidth available in the tissue. But what is the bandwidth of the tissue? So for this, let's first talk about the composition of the tissue. The tissue is composed with cells, and cells has membrane. The membrane is a capacitor. If we apply ionic current in the tissue, low frequency ionic current is going to flow around the membrane, and you will see lower conductivity. And when we increase the frequency of the ionic current, it's going to pass through the membrane, past the capacitors, and you will see the content inside, and you will have a higher conductivity level. We could model this with simple RC circuits, as I present with the COPO model, and from this with RC model, you can expect there should be a low frequency bandwidth limitation. But what is this bandwidth limitation? So here we also try to do the experiment with 2 electrode pair placed in between the pork tissue here, the biological tissue, and then we try to change the frequency of the ionic current. And here is the path loss we measure. And interesting is that you can see there's indeed a low pass bandwidth response, which is in the order of hundreds of megahertz. We also they indicate that there is sufficient bandwidth for us to perform the communication up to hundreds megabit per second. We also noticed that when the frequency is too high, they start to have a ringing in the frequency response. That means that it's becoming transferred into the radiate behavior, and that's a region we also try to avoid. So we use this tissue measurement result to design the impulse body channel communication. Here we don't need to have a large antenna, so we can reduce the module area to 25 millimeter square area. We also try to perform the communication, the bit communication, and reach up to 250 megabit per second. And very important is that energy consumption is very low, down to 2 picojoule per bit, because it does not drive the low impedance antenna. This is even 10 times lower power than the impulse radio ultra wideband. Okay, next, I would like to talk about the data reduction. And here we will especially talk about neural event-based encoding. So there are a large amount of data we want to reduce, but without loss. And here I would like to especially be inspired from retina and optic nerve. So our retina is equivalent to a camera with up to very high resolution, high fidelity, up to 500 megapixels. If we want to transfer this data, you will have a data rate up to 1 terabit per second. So the question is that how can a tiny optic nerve linking between the retina and the backside of the brain called visual cortex being able to handle such high amount of data transfer? One number I would like to share is that with a high-speed Ethernet they can transfer 10 gigabit per second. They will already generate, typically consume watts of energy. And now we are talking about 1 terabit per second. So there must be something that can be inspired from the biology. So here is how the secret is that how retina encode the signal. So it's actually here is the way the retina encode the signal. It only gives the binary outputs when they see larger enough changes. So this can greatly reduce the data rate, and it's our brain that recovers such, reconstructs such image back to the image that we think we see. Also in 2008, the ETH group, they also used this concept to apply into the camera called dynamic vision sensor that also greatly reduce the data generated. Okay, now here I would like to talk a bit more about the event-based sampling, but first let's talk about more traditional frame-based sampling, also we call micro-sampling. In the frame-based sampling, we have a fixed clock, a fixed frame rate, and each frame it will provide multi-bit outputs to represent the amplitude information. But in the event-based sampling, on the contrary, there's no clock. So it only gives a binary outputs when they see larger than sufficient large change. You can have the output can be 2 bits. One indicate going down and one indicate going up. So such kind of event-based sampling is very suitable to apply in the signal that is very sparse, including the extracellular neural recording. Neuron fires only a few times per second, and each firing only lasts for hundreds microseconds. If we apply such event-based sampling to the neural signal, we are able to reduce the overall number of bits up to hundreds to thousands of times. It is because that the information is stored in between the binary bits instead of multi-bit information. Such event-based sampling can also be implemented in the circuits. In dynamic vision sensor camera, they have a differentiation circuits embedded inside the pixels. We can also use a special type of ADC called level crossing ADC to perform such event-based sampling. So the function is as shown here. You have a 2 threshold voltage. If the input voltage crosses one of this threshold voltage, it will trigger the output binary event, either up or down. And this up or down event is coming back to adjust this threshold voltage V high or V low, V out of that, as the waveform shown here. Next, I would like to talk about one challenge when you have a multi-channel event-based sampling. So, but again, let's first look at how can we serialize the data on the frame-based multi-channel sensors. Serialization is important for communication, either wireless or wired. For wireless, you want to share the media. In wire communication, you also want to reduce the number of wires. One example with IMAX and NeuroPixels, there are 384 recording channels, and each channel has 10 bits, and you will need 3,140 wires if we don't do any serialization, and 300,000 wires. Routing that around the brain will not be practical. So they use a time multiplexing approach to reduce the number of wires from 3,000 to just 8 wires. And time division multiplexing is a very standard way to serialize the data from frame-based assembling multi-channel sensors. You will rotate selecting the signal from different channels and sequentially sending out. For this, you will need to have a much higher sampling frequency clock and also a protocol to define when you're going to send out which channels. But typically, this approach has a very low protocol overhead. The problem is that if we want to serialize the asynchronous events coming from event-based multi-channel sensors, then there will be issues. On one hand, we want to preserve the time information of the events. On the other hand, each channel, each event should indicate it's coming from which channels. So neurons also received a synchronous spike from thousands of other neurons with a structure called dendrite with a very dense connection. But we cannot do this with electronics because of the limited fan in and fan out. Instead, we can leverage the speed of electronics, of nanoelectronics, and the protocol, a similar time division multiplexing protocol, also exists in the standard event-based computing called address event representation. So each event will attach the address, the channel address from the source. And you can imagine such AER can introduce quite high overhead, and also it will become a time uncertainty in an event transmission system. And here I would like to talk about the impact of this time uncertainty in a reconstruction. So to reconstruct the signal from the event-based sampling can be done with simple accumulation. If you receive up events, you just accumulate up, and vice versa. With down events, you accumulate down. But if there's a time uncertainty exists in this reconstruction, it's going to degrade the quality, especially it will degrade the signal to quantization noise ratio. And here we also try to perform a numerical analysis with a simulated SQ and R versus time uncertainty. We also compare with the compression ratio. So from our analysis shows that if we want to achieve high SQ and R, meaning that you should have much more events generated, with more event generated during the reconstruction, that means the time uncertainty also should become more challenging. And also more events will also reduce the compression ratio. And such time uncertainty, one dominant part is come from this AER protocol mentioned previously. Also, the conversion speed of level crossing ADC, the resampling sampling frequency during the reconstruction can also affect the time uncertainty. It's important to know that the extracellular neural recorded signal typically is a SNR below 20 dB. So we should design a event-based transmission system with a time uncertainty below 10 microseconds, such that we can achieve a SQ and R higher than 25 dB. This can avoid to degrade the overall SNR. So 10 microseconds will be the target for our system. Now, I would like to talk about another topic that is a spike classification. So in many BCI systems, it's actually no need to transmit the full spike waveform all the time. Instead, the energy consumption, the device volume, and even the latency of the BCI is even more important. If we can perform the spike classification, as mentioned previously, each recording channel will pick up spike from multiple neurons. If we can perform the classification locally on the implants, real time, they can greatly reduce the data and help to reduce the energy consumption. But there is the important trade-off is communication versus computation. So let's first look at the typical processing pipeline of the spike classification. With the recording data, we need to perform the filtering. So remove the low frequency fluctuation and high frequency noise. Then we can detect a spike, typically with a simple threshold voltage, and then we window the spike. We do the feature extraction to extract the represented features such that we can reduce the dimension. And then with sufficient large amount of data, we can group the spikes with a similar features as the clusters. And then once we have a new coming spike, we can assign that to a corresponding clusters. This is a classification. The result of classification can be further processed for either neurostimulation or prosthetic control. Since the intra-cortical neurosensor should be implanted, so which point of time we should transmit all the data is a question of the is a trade-off between the communication and computation. So we can transmit the data, raw data, just after the filtering. This means that we still have a high amount of data, and then this will have a high communication requirements. And wireless communication is typically the most power-consuming part of the whole implants. This will lead to energy waste. We could also transmit once we perform all of the classification. This means that all of this computing step will be done on implants, and you can imagine this is going to have high computation requirements, and especially the data storage, because for performing clustering, we need to have sufficient large data. And then large data storage means that you will need to have a large chip area and also high memory access energy. Also, accuracy is a concern because cluster can drift over time. And actually, in the neuroscience community, there is still lack of golden standard. What is the best way, optimum way to perform the spike classification? And if we take a closer look at this processing pipeline, the part that require highest computation and storage requirements is this clustering step. So one question would be, can we try to avoid to perform clustering on the implants such that we can have a better trade-off between the communication and computation? So one method, alternative method, is the feature transmission. Since we know that clustering is the computing and storage bottleneck, we can transmit the data right before it. Just transmit the features. Because features extraction is to extract the represented dimension. So it does not require as large data as clustering, so we can reduce the storage requirements. Also, the feature dimension does not drift a lot over time. So this also alleviates the drifting issues and improve the accuracy. Compared to transmit the raw data, we can reduce the data by already around 100x. And compared to perform clustering on the implants, we also gain much better accuracy because there are less drifting issue. And typically, the feature extraction is done offline with a machine learning method, principal component analysis. But the PCA is difficult to implement on implant and perform in real time. Instead, recently, more and more neuroscientists, they try to use geometric feature extraction based on waveform. So one example shows that if we can extract just duration of the spike, meaning that from the peak to the valley, you can already nicely separate two neurons. And this paper also shows the benchmark of the several feature extraction methods with classification error versus hardware complexity. And this part based on the feature extraction based on the derivative, either first order or second order, they shows very low classification error, and at the same time, at least 2 order lower hardware complexity compared to standard PCA. Okay, the second alternative method is to have a dual mode operation. This is similar to many edge AI systems that require low latency. For example, the self-driving cars with autopilot. So in this dual mode operation, we have offline training mode and also online classification mode. During the offline training mode, we transmit the raw data and then we perform the clustering in the external computers, and then we try to build the templates. Then we transmit back these such templates to the implants. During the online classification mode, we use this template to perform template matching and classification. And this has a very important benefit is that it has low latency, which is sometimes very important for many BCI applications. And once in a while, we need to retrain the model. So in order to accommodate, for example, drift issues. For a real-time spike classification, we can do either with template-based matching or feature-based matching. And for template-based matching, we have local storage of the template waveform, and then we try to perform the classification by measuring the distance. And you can imagine with the number of channel increase, this will have also higher storage requirements. We can also use a feature-based matching by first extract the features. For example, in here, we use a geometric features extraction, and then we try to match the features. For this, you will require less storage space, but you will need a bit more computation in advance, and this will also slightly increase the latency. Okay, now next I would like to talk about this trade-off between the communication and computation in spike classification with one example of nerve conduction study. Nerve conduction study is a very important diagnosis tool to understand the condition of the nerve. And our nerve, peripheral nerve, is a highway connecting our brain and our body. And typically they have up to hundreds of axons that is propagating the spike in the nerve. And usually we use such kind of nerve cuff, which is non-penetrating, minimum invasive nerve cuff, to record the spike. Since we have many axons there, the spike we record is called compound action potential. We can measure the conduction velocity by having two cuff electrodes with a certain distance d along the axon, and then we measure the conduction latency, the spike propagating between these two electrodes of the latency of delta t. With delta t and d, we are able to estimate the conduction velocity. And in many cases, we try to do this under the stimulation, also called evoke compound action potential, ECAP. The neuro-telemetry for the nerve conduction study, which include readout circuits, A to D, and to digital conversion, signal processing, and wireless transmission, should have certain requirements. First is that it should be able to identify or classify the desired ECAP, but not any random spike coming from the artifact or other spontaneous ECAP, the compound action potential. Second is that the conduction velocity can be as high as 100 meters per second. If we want to design a miniature cuff, a nerve cuff, then the neurotelemetry should have a temporal precision down to microsecond level. It is important to know that in the frame-based sampling, even with tens of kilohertz of sampling frequency, the temporal precision will still be limited to tens of microseconds. Finally, we want to do this nerve conduction study all with a tiny implants. That means that we have power and volume constraints. That is very important that we need to carefully trade off between the communication and computation. So here we try to propose the neurotelemetry for D, we are able to convert the signal to the events, and they can help to greatly reduce the data by several hundreds of X. This reduces the burden for the further communication and computation. In the dual mode operation, in the first mode is diagnosis mode, which is we use that for data analysis and also building a model. In some application, this mode is even mandatory. In this mode, we serialize the events generated by the level crossing ADC with the AER encoder, and then we transmit out with body channel communication, which does not require large antenna. With this event-based transmission method, we can reduce overall data by 125x. In the second mode, ECAP classification mode, we try to use the model built in a diagnosis mode to perform template matching. And here we want to show you we use a spiking neural network as the classifier. And this SNN has a feature of low energy consumption, low latency, and microsecond of temporal precision. This slide, I would like to show you a bit more how we use a spiking neural network to perform the ECAP classification. So spiking neural network has a feature of a very low energy consumption because first, it computes on demand. Only when you have events, it performs computation. The rest of the time is quiet. It also does not require modification, which also reduces the hardware complexity. Second is that it computes in time domain, meaning that you can achieve potentially achieve very low latency and also fine temporal precision. So here shows the typical ECAP waveform, which include the depolarization, repolarization, and hyperpolarization. If we have used the level crossing ADC to first convert this waveform into time domain events with up and down events, then we can send this to the spiking neural network. And the spiking neural network perform the computation similar to the biological neurons. The biological neurons can perform computation when they receive either excitatory or inhibitory spikes that can change the membrane potential. And once the membrane potential reaches certain threshold, it fires. And with a similar approach, we can train the SNN to recognize the temporal features, including, for example, peak or valley. Then we can extract the duration. We can transmit directly out these temporal features, similar to the alternative method I mentioned. First alternative method mentioned in the previous section with feature transmission. We can also directly do the template matching to classify the full spike waveform, like the second alternative method that we mentioned. So here shows the characterization result of the ECAP classification. The characterization is done first. We record the ECAP from an earthworm, which is a very common textbook approach. The earthworm has a single really large nerve that is easier to record and stimulate. With this record ECAP, we send it to the waveform generator to generate a synthetic ECAP, and then we send it to the neural telemetry. We train SNN to recognize such pattern, and then we continuously input such synthetic ECAP. The SNN classify that and shows that it has a below 10 microsecond of classification precision. On top of that, you can also see it has a very low latency, and from our measurement result shows higher than 99% of classification rate. Here, I would like to show you also the event-based communication. So we use AER encoder to serialize the events. And this AER has up to 8 addresses that can represent different events or features in different modes. In diagnosis modes, we can represent up or down events from 2 different channels. And in the ECAP classification mode, it can represent different features. We also show you here is the body channel communication transmitter. Here we use edge bridge structure, which we inject or sink the charge to create ionic current. And this is a bit similar to the stimulation circuits. So we have to carefully balance the charge to avoid potential tissue damage. And to balance this, we encode with Manchester code, which each bit represent with an alternate bits, and then finally coded with a ternary encoded. Here shows the measurement result. Again, we input the similar synthetic ECAP waveform to the neurotelemetry, and the level crossing ADC convert the signal to an up or down event. And each event will generate an AER packet to be transmitted by the body channel communication transmitter. And here we can zoom in further to look at each AER packets, which contains 6 bits, as shown earlier. And the each AER packets is roughly around 6 microseconds. And as mentioned earlier in the numerical simulation, we try to avoid the timing uncertainty created by AER higher than 10 microseconds. So here we also try to reconstruct the signal and try to estimate such reconstruction error, and you can achieve a 4% RMS error, which equivalent to a 25 dB SNR, SQNR, which matched to our previous analysis. Now, I would like to summarize the performance of this neurotelemetry and also benchmark with other literature. In our present neurotelemetry, especially for nerve conduction study, we have a dual mode operation with classification mode and diagnosis mode. We use event-based, neuro-inspired event-based sampling, which can achieve the data compression ratio up to 125x. We also have a neuro-inspired spiking neural network to perform the feature labeling and also the full spike classification, and has a record of temporal precision down to 5 microseconds. With this neuro-inspired approaches, we achieve at least 10x lower power and overall module area. Finally, here I would like to conclude. So in this talk, first we talk about the wireless communication for the brain-computer interfaces. The neurotelemetry should have a smaller area in order to minimize the invasiveness. It should have a low power consumption such that it can reduce the tissue heating, avoid tissue heating. All of this at the same time, we have to maximize the data rate such that we can interface with more neurons. Also, we talk about the neuro-inspired approach. We should try to learn from the neuroscience to build a technology that is more neuro-inspired. Also, we call neuromorphic engineering, such that with this better neurotechnology, we can help to further advance the neuroscience or therapeutics. And here we introduce 3 neuro-inspired approach: body channel communication, event-based sampling, and also the spiking neural network. Also, we talk about the trade-off between the communication and computation for intra-cortical neural data. And here, communication and computation has its trade-off, its pros and cons. We also talk about with the spark classification, we have 2 alternative methods to have a better trade-off between them. One is a feature transmission, and another one is dual mode operation. We also use a conduction velocity study with the implant to show this trade-off with a neuro-inspired approach. Thank you for your attention, and if you have any question,